Hello. Hi. I'm going to talk about my payload for the OpenBSD IPv6 remote MBUF overflow. This bug was found and researched by Alfredo Ortega at Core. So he deserves the great credit for finding this bug. The vulnerable code differs a bit in the various OpenBSD releases, so I focused only on 3.7 up to 4.0 in my implementation. The bug is triggered by sending specially crafted ICMP version 6 packets, which causes complete MBUF structure to get overwritten. And I won't go into details about taking control of the execution flow when controlling an MBUF structure, since Christer already talked about that. There are some other ways to control the flow as well. But the proof of concept code overrides the ext3 function pointer. And when ext3 is called, ECX and EBX and ESI all points to the start of the overwritten MBUF. So jumping to ESI makes us end up at the start of the overwritten MBUF. And from there, we jump backwards about 200 bytes to reach stage 1. So my payload has 3 stages. Stage 1, which installs a backdoor, and that's a wrapper for the ICMP6 input function. We use this function since we send ICMP6 packets to trigger the vulnerability. So we know that we can reach the target system if the exploit succeeded. The stage 2 is the actual backdoor, the code that wraps the ICMP6 input function and listens for incoming packets and check for backdoor commands. I implemented 4 different stage 3 commands. We'll go through them later on in this talk. The first thing that stage 1 does is to locate stage 2. Stage 2 is sent in a previously sent ICMP echo requests packet, version 6 of course. And when ext3 is called from within the m3m function, we have a pointer to the MBUF chain for the previous packet at 108 bytes from ESP. So all we have to do is traverse that MBUF chain to the end and fetch the data pointer in the last MBUF to get a pointer to stage 2. Sometimes during heavy network traffic, it might be possible that another packet is the previous packet. So there are some checks as well to make sure that it's actually the stage 2. For example, there are some magic bytes in the beginning of the payload, and I check the pointer on the stack that the high order byte is the same as the high order byte for the overwritten MBUF, and check various MBUF flags and stuff like that. So, but it works most of the time. Sorry. The stage 2 also contains a symbol resolver. So stage 1 calculates the address to the symbol resolver, which is an offset from the start of stage 2. We'll talk more about the symbol resolver later, but now that we can resolve symbols, we resolve the INET6 SV array and fetches the address of the current ICMP6 input function, since stage 2 need to know this. We make sure that the backdoor is not installed. Well, you might want to upgrade or something, but I didn't implement it in that way. So we check for the backdoor, and if it's not installed, we simply clean up the stack and return. The backdoor does not start with the traditional saving of the frame pointer, but with a call instruction to get its current location, so that we can fetch so-called arguments, which is prepended to the code. And that's, for example, the address to the real ICMP6 input function. So it's enough to compare the first 4 bytes to see if the backdoor is installed or not. Since we can resolve symbols, we resolve malloc, and we allocate kernel memory for stage 2 and copy the code there. We then wrap the ICMP6 input function by overwriting the function pointer inside the init6 SV array. And we can do this without raising any locks, since all the locks we need are currently in place because we came from an interrupt. And when the backdoor is installed, we just clean up the stack and return. So now we have the backdoor in place, which listens for all the incoming ICMP6 packets. The symbol resolver part of stage 2 is really nice, and all the stages uses it. It saves a lot of trouble because we don't need any hard-coded addresses to symbols. The ELF header is not mapped at a fixed address on OpenBSD, as for example on FreeBSD. But my colleague you will notice that it was mapped right after the BSS segment, so we simply scan for the ELF tag from there to find it. And then we look up the symbols pretty much as you do in any Windows shellcode by comparing hashes of symbol strings in the DINSYM section. The ELF symbol resolver that I use in my payload was initially written by Christer for another project, so the code was modified a bit and later used in this code. Stage 2 simply listens, as I said, for ICMP6 packets with magic bytes indicating that it's a backdoor command in the payload. It then copies stage 3, the backdoor command to run, to allocated memory, and wraps the system call with this command. It then calls the real ICMP6 input function and return with a return value from that function. Okay. To be able to perform syscalls from within the kernel is really nice. It opens up and it makes it really easy to write kernel shellcode and highly portable. So my code works on all the releases. There's nothing different between them. The thing is that we need a process context to be able to use system calls. And we came from an interrupt, so we don't really have that. So we wrap a system call, and when the system call is called from a process, we fork from this process to create a new process to play with. I looked a bit at the default installation in the source code, and the get time of day was called quite frequently, so I used that one, and it works good. The state 3 command needs to know which system call we wrapped to be able to call it later on. The index is enough, since we can resolve the sysint table and later on. The address of the real handler of the system call is also, as well as the index, prepended to the state 3 command and can later be extracted from an offset of the value of EIP. So I implemented 4 different stage 3 commands. The traditional TCP connect back, which spawns a shell, a raw shell. We might want to be able to change the secure level, such as for loading kernel modules later on. So I implemented a command that allows us to set the secure level to an arbitrary value. Depending on the system that we are attacking, it might be firewall rules and stuff like that preventing us to create the connect back connection. So we need a way to modify the rules. So I implemented a command for us to run arbitrary shell commands, just as the system function in the C library. We won't get any output from this command, obviously. So the standard out and error is sent to the output of the process that calls get time of day, which we wrapped. So just have to make sure to redirect it to device null or wherever when you type it on the command line. The last command uninstalls the backdoor. I don't know why you want to do that, but I needed it while testing and developing, so it's still in there. It would have been nice with with some commands for transferring files as well, but I didn't do that. It works with the traditional old Unix commands once you have a TCP connect-back connection. The stage 3 commands are all implemented in similar ways. They all use the stage 2 resolver to resolve symbols. And the first thing they do is to reset the wrapped system call with a real value, so that the correct handler handles the next call to the wrapped system call. We don't want it to be called more than once. It then calls the real system call, saves the return value so that the calling process won't detect that we used it to create a new process. It then forks from the calling process to create the process that actually does the stuff that we wanted to do. Before we start connecting back or whatever we're supposed to do, we have to make sure that we run with root privileges. Since any process can call the wrapped system call, we have to just simply set the real user ID to 0 before continuing to do whatever we want to do. And just simply terminates the process on failure. We control the forked process in kernel memory, so we simply point it to a function where it starts executing and run the system calls we need from there. For example, socket, connect, and stuff like that. I have some technical problems with my hardware, so I was going to play a VMware recording of the exploit in action instead. It will be available anyway, so you can play around with it yourself. We will be attacking OpenBSD 4.0 here. So we resolve the MAC address and starting to attack. So now the vector is installed in kernel space, running there, looking at every packet arriving to the ICMP6 input function. I don't have any firewall rules and stuff like that on the machine here, so we just simply create the connect-back connection, the first thing we do. So what happened there was that we sent this single ICMP6 echo request packet containing the code, the stage 3 command for connect back, and waited for get time of day to get called. And when get time of day was called, it connected back to us and created this shell. We continue to check the current value of the secure level, which is 2, the highest possible. We then check in the temp directory just to see it's empty. We then exit